Hello, Matthews Gatos here. In this video, we will cover section 9.2, but before we do that, let's review 9.1. So in this question here, I want to state asymptotes, intercepts, write the equation in transformed form, and describe the transformation. We'll put all that information together and then we'll graph it. So let's first of all start with the fraction and all those tricks we know for fraction form. So in the numerator here, I know that if I set that equal to 0, I will get the x-intercepts. So I know that the x-intercept is going to be 3 over 2. If I set the denominator equal to 0, I will get my vertical asymptote because I can't divide by 0. Vertical asymptote, -2. If I look at the ratio of the leading coefficients, because the degree of the numerator is equal to the degree of the denominator, I will get the horizontal asymptote. And that's y equal 2. So horizontal asymptote, y equals 2. Okay, and then if I look at the ratio of the constants, that will give me my y-intercept. So the y-intercept is -3/2. So looking at these, I can already tell some parts of the transformation. So normally my vertical asymptote is at 0, but now it's at -2. So that tells me that I've had a horizontal translation 2 units to the left. My horizontal asymptote of 2, normally it's at 0, so I also know there's been a vertical translation 2 units up. So for the stretch and the reflection, I need to write my equation in transformed form. So I'm going to use long division to write this in transformed form. So x plus 2 into 2x minus 3. So 2x divided by x is 2. Multiply them together and I get 2x plus 4. And then subtract. 2x take away 2x is 0. -3 take away 4 is -7. So I know that this equation is going to be 2 and subtract the remainder 7 because it's negative out of x plus 2, or write it as -7 over x plus 2 plus 2. Now I can see that my a value is -7. Once I know that, I can figure out my stretch and my reflection. So because it is negative, I know there's been a vertical reflection in the x-axis, and the value, the absolute value of a is 7, which tells me there is a vertical stretch about the x-axis by a factor of 7. So let's put all of this information together in a graph. Okay, so I have my x-intercept. I'll plot my y-intercept. I'll plot my vertical asymptote and my horizontal asymptote. So looking at this, this is a transformation of a 1 over linear. So I know that it's going to be 2 pieces, half of the sections, and I know that they are going to be reflections of one another in the vertical and horizontal asymptote. So I know one of the pieces will be down in this area because that's where my x and y intercepts are. So I know that coming up with the graph of this, it's going to connect these two, come up and hug the horizontal asymptote, and come down here and hug the vertical asymptote. So that's my first part. I know that the other part will be in the top left-hand corner because I take this graph here, reflect it in the vertical asymptote, and reflect it in the horizontal asymptote. So something like that will be what my graph looks like. Okay, so in this lesson, we're going to look at 9.2, analyzing rational functions. And this is going to be where I have polynomial in the numerator, polynomial in the denominator, not necessarily linear factors. So I just want to review with you the tips, especially for the asymptotes. So for a vertical asymptote, it is based on the restrictions of the denominator. So a vertical asymptote is something the graph can get close to, but it can't cross or touch. Horizontal asymptotes are a little bit different. Those are where the ends of the graph approach. So there's 3 different types of horizontal asymptotes we can have. And it all is related to the degree of the numerator and denominator. And by degree, I mean the highest exponent of x. So the first case, if the numerator and denominator have the same degree, and that's what we did in the last section, the horizontal asymptote will be the ratio of the leading coefficients. And then if the degree numerator is less than the degree of the denominator, that's like what we did in 20-1, the y-axis, or y equals 0, will be the horizontal asymptote. And a new one here is when the degree of the numerator is bigger than the degree of the denominator, there is no horizontal asymptote. So I just want to take a minute and look at these horizontal asymptotes in a little bit more detail, and I have an example of each type so you know what I'm talking about. So in the first one, the degrees are equal. So something like a linear over a linear. Now, I'm interested in what happens at the ends of the graph. So let's make x a really, really big positive number. If I do that, I'll have 2 times a really big number, subtract 3, over 3 times a really big number, add 1. So if I have a really big number and I subtract 3, it's really not going to affect it. If I have a really big number and I add 1, it's not going to affect it. So this is really the same as 2 times a really big number over 3 times a really big number. And you can see, looking at these, the ratio is just going to be 2 over 3. 2 times a big number over 3 times a big number just ends up being 2/3, which is the ratio of the leading coefficients. Okay, second case was where the numerator degree was less than the denominator degree. So something like this. So again, let's take that idea. Ends of the graph, that's what a horizontal asymptote is. When x gets really, really big, where is y going? So if I have 3 over 3 times a really big number plus 1. Okay, well, if I have a really big number and I add 1 to it, it's still just a really big number. So if I have 3 over 3 times a really big number, well, the 3's cancel out, and that's like saying 1 over a really big number. So as I make my denominator bigger and bigger and bigger, 1 over that big number will become a really small number, and it will approach 0. So that's why, in this case, the horizontal asymptote is 0. Now this last case is new to 9.2. Let's look at that, where the degree of the numerator is bigger than the denominator. So something like this. So imagine again, ends of the graph, I have a really big x value, and I have something like that. So if I have 2 times a really big number and I subtract 3, it's not really going to affect the graph at all. Okay, so imagine I have 2 times a really big number and I divide it by 3. It's still going to be a big number. So this is just going to continue growing. It's going to be a little less big, but it's still going to be big. It's not going to approach a specific value. So since it's not approaching a specific value like this one and this one, we say that it does not approach a specific value because there is no horizontal asymptote. So that's where I'm going to see the ends of the graph not approaching a specific value. Okay, let's look at an example. So in this example, I want to state the equations of the asymptotes, y and x-intercepts, domain, range, and then sketch a labeled graph. So in this case here, I have a linear factor in the numerator. I'm going to factor the denominator, x minus 4, x plus 2. Okay, that can't be simplified any further. So looking at this, I can see that I have a vertical asymptote at x equal 4, and I have a vertical asymptote here of x equal -2. So I'm going to put both of those on the graph to start. So vertical asymptote at -2 and vertical asymptote at +4. Okay, looking at the numerator, I can see that I have, oh, let me change my color here. There we are. I can see that I have, if I set this equal to 0, I have an x-intercept at 1. So I can plot that x-intercept at 1 right there. Okay, looking at a y-intercept is where I don't have any x values. They set to 0. and it's just the ratio of the constants, which would be negative 1 over 8, negative 8, which is just positive 1 over 8. So just this tiny little y-intercept there. Okay, let's look at horizontal asymptotes. So if I look at those rules that we went through, the degree of the numerator is 1. The degree of the denominator is 2. So since the degree of the numerator is less than the degree of the denominator, I am going to have a horizontal asymptote at y equals to 0. So horizontal asymptote there. Okay, now this is the first time that we've seen a graph that has more than 4 sections. You can see that there are 6 sections. So I know that there's only graph in half of the sections. So not a lot of information to go on here. So what I'm going to do is, I see that what my sections are. I'm going to look at my graphing calculator to kind of help me come up with the shape of the graph, because I have 3 different sections. So when I put this into the graphing calculator, that's what my graph looks like. And I can see my 3 different sections and the horizontal asymptote in the middle here. So I know that that's what the sketch of the graph looks like. So let me just come back over here and plot those values again. So my x-intercepts, my y-intercepts, and then my asymptotes. We'll put those back in together, and then we can sketch. So we're coming, the end behavior is going to the behavior around the vertical asymptotes is going to go towards positive and negative infinity. And then I had these ones here. The end behavior always goes towards the horizontal asymptote. This will hug down the vertical asymptote. Again, ends of the graph go to the horizontal asymptote, and this will come up here. This is an example of a graph that you can see crosses the horizontal asymptote, but it does so in the middle. But again, a horizontal asymptote is where the ends of the graph, really big X, really small x, where those approach. So the only thing I have left to do in this question here is state the domain and the range. So the domain will be the set of all x such that x cannot equal to negative 2 or negative 4, but is still an element of the reals. Now, normally we would say for the range that the range would be y can't be 0. But remember I said to you for horizontal asymptotes, you always want to look at the graph just to see if, as in this case, it does cross. So because it does cross the horizontal asymptote and these ends extend infinitely in both directions, I know that the range is just going to be the set of all y such that y is an element of the reals. Okay, let's try another graph. So this one here. So I want to state the equations of the asymptotes, the x and y intercepts, and then domain and range, and do a labeled sketch. Okay, so for this one here, I'm going to factor my numerator, x minus 3, x plus 2, and then I leave my denominator. Okay, so the x-intercept is set the numerator to 0, and you can see your x-intercept. So x minus 3 becomes an x-intercept of positive 3. X plus 2 becomes an x-intercept of negative 2. Y-intercepts are the ratio of the constants. So if I get rid of my x values, it's just the ratio of the constants. So negative 6 over 8, negative 8, in lowest terms is 3/4. So my y-intercept is 0 and 3/4. Okay, vertical asymptote, I look towards the denominator because I can't divide by 0. So x minus 8 can't be 0, which means I have a vertical asymptote at x equal to 8. Horizontal asymptote. The degree of the numerator is 2. The degree of the denominator is 1. Since the degree of the numerator is bigger, there is no horizontal asymptote. So what that means is the ends of the graph will not approach a specific value. So I'm going to put this together on a graph. So I have a graph here, and I have some points that are going to help me out, a maximum point and a minimum point, because this graph is a little different than what we're used to seeing. So let's plot what we already know. We already know I have an x-intercept at 3, I have another one at -2. I have a y-intercept at 0 3/4, so right about there. I have a vertical asymptote at 8. We'll call this one here. And another one, oh no, that's the only vertical asymptote, and no horizontal asymptote. So my graph has two sections. And because there's only two sections, it's not bounded by a horizontal asymptote, I'm going to expect to see graph in both sides, and I can see from my points, my max and my min, which I did use my calculator to figure out, I know what the graph is going to look like. So I'm going to always go towards -infinity for the vertical asymptote on this side. I'm going to connect these dots here. That's the highest point there, so it's going to come right back and go down. This point here is the lowest point. So again, the end behavior always goes towards the vertical asymptote. And then this one here, since that's the lowest point, it's just going to come right back up because I can't go any lower than that. Again, you can always put these into your calculator just to give like a little idea of what the graph will look like, but I'd want to see all of those important points on it. So looking in the graphing calculator, I can see that's a pretty reasonable graph. Okay, let's look at another case of a rational function. So I put this into my calculator, x squared plus 5x plus 6 over x plus 2, and not what I was expecting to see. I see a linear graph. So I want to examine this a little bit closer and say, why is that a linear graph? Why is it just a straight line? Because we have not seen anything like that. Well, I know in the denominator here I have an x plus 2. Now x plus 2 can't equal 0, which means x can't be -2. But if x can't be -2, doesn't it look like it's passing through -2 at that point? That's a little bit confusing to me. Why isn't there a vertical asymptote at -2? So I want to know what happens to the graph at that point. Why is there not a vertical asymptote at -2? So what I did is I put this in my calculator and I really zoomed in to see what's happening at -2. And when I did that, I can see that there is an actual break in the graph. It is discontinuous. What I mean by that is to draw this graph, I would come up to this point here. I would have to lift my pencil off and continue going on because there's a break in the graph. So there is a hole in the graph, and you can even see in the table of values, there's an error in the graph when x equals -2. So why is there a hole in the graph? But I didn't see that originally. Well, let's look at this equation and let's factor. I'm going to factor the numerator. I see that there is a common factor that is removable. So here, this is a removable factor because it's common to the numerator and the denominator. So I'm just left with x plus 3. That's what the graphing calculator originally graphed. It graphed a linear function. The calculator knew that there was a hole in the graph, but we didn't really see that. So the graphing calculator graphed this linear function, but it knew that x could not be -2. Well, if x can't be -2, let's put it in here and figure out what y can't equal. So if x can't equal to -2, then y can't equal to -2 plus 3, which is +1. Putting those two together, I have a point of discontinuity at -2 and 1. So anytime I have a removable factor like that, I will have a point of discontinuity. So really what that means is this function, the rational function, simplified to be x plus 3. In the simplified function, if x was -2, then y was +1. So that's why there is a point of discontinuity, just meaning a break in the graph, a hole in the graph at -2 and 1. So a point of discontinuity is any point xy where the function is not continuous. And that happens anytime there's a common factor to the numerator and the denominator. we can show this graphically with an open dot. So we have to be aware that that's there, because the calculator, unless you zoom in on it, won't show you that. So let's try an example here. So the very first thing that I do is I just factor my numerator and, if possible, my denominator. So I have x plus 4 times x minus 2 all over x minus 2. Now I know that x can't be positive 2, because if it was, I would be dividing by 0. State your restrictions before you simplify. Cancel those out, and I'm left with x plus 4. So x plus 4 is a linear function. It has a y-intercept at positive 4, an x-intercept at negative 4. But I know it too, there's a hole in the graph. Let's figure out what goes with it. If x can't equal 2, then y can't equal, put the 2 in for x, y can't equal 6. So that means at 2 and 6, there is a point of discontinuity. So I'll really exaggerate that with a big open dot. And this is a linear function, so just kind of connecting the dots, I know my graph would look like that. Okay, let's compare these two graphs. Compare means tell me how they are the same and also how they are different. So for this one here, let's factor. F of x is x times x minus 3 over 2 times x plus 3. G of x is x times x plus 3 over 2 times x plus 3. So same denominator, different numerators. I want to talk about how they're same and different. So let's talk about how they are the same. So I see they both have a common factor of x in the numerator, which means they both have an x-intercept of 0. Let me write that right in the middle. Okay, so how are they the same and how are they different? So this one here I will write in the middle because it's how they are the same. So they both have an x-intercept at 0, 0. Okay, if it passes through the origin, that also means that the y-intercept is also 0, 0. So that's something else they have in common. So they both have x-intercept at 0, a y-intercept at 0. The other thing that they have in common, the degree of the numerator is 2. The degree of the denominator is 1. And since 2 is bigger than 1, that means that both of these graphs have no horizontal asymptote. So that's how they're the same. Let's talk about how they're different. So in f of x, I have a vertical asymptote at x equal negative 3. I also have this additional factor here, which means I have another x-intercept at 3 and 0. Okay, at g of x, these are removable factors. Now x still can't be negative 3. So if x can't equal negative 3, then look what I'm left with. I'm left with x over 2. Then that would mean that y can't equal 3 over 2. So this graph has a point of discontinuity at negative 3 and 3/2. So that would summarize how they are the same and how they are different. Okay, so to recap, graphs will have a vertical asymptote if the factors in the denominator are unique. In other words, they're not a removable factor. Graphs will have a point of discontinuity if factors in the denominator are common factors to those in the numerator. Now, graphs can have both a vertical asymptote and a point of discontinuity. That's important to note. Okay, let's look at this example. Determine the equation of a rational function with a point of discontinuity at negative 4, negative 6, and an x-intercept at 2, 0. So let's focus on this one here first. If they have a point of discontinuity at negative 4, negative 6, that means that x plus 4 has to be a common factor. That's the only way you can have a point of discontinuity, is if you have a removable factor. So I know x plus 4 has to be on the top and the bottom. Okay. I also know that I have an x-intercept at 2 and 0, which means I have a factor in the numerator of x minus 2. So for these graphs here, I always told you have to solve for a. So I don't know what my a value is. Well, this function in lowest terms would be a times x minus 2. So let's plug in that point of discontinuity, because that's a point the graph passes through, to solve for a. So y equals a times -4 minus 2. So -6 equals a times -6, which means my a value is 1. So putting it all together, the equation that has a point of discontinuity at -4, -6, and an x-intercept at 2 would be this function here. Okay, last question I want to do is when I give you a graph and I ask you to come up with the equation. This is a perfect example of a graph that has both a vertical asymptote and a point of discontinuity. Now, this point of discontinuity is at 3, and I'm really not sure what. So they don't tell me what it's at. But I don't really necessarily need to know that. Let's look at what else I have. I have an x-intercept at -2. I can see the ends of my graph are approaching this horizontal asymptote at 2. Okay, I think that's enough information for us to do the equation of the graph. Okay, so looking at this, vertical asymptote of x equal to -1 means I have a factor of x plus 1 in the denominator. Point of discontinuity at 3 means I have a removable or common factor of x minus 3 in the numerator and denominator. X-intercept of -2 means I have a factor of x plus 2 in the numerator. And then the last thing, remember how I said you always solve for a? So you can solve for a, or you can use the rules of horizontal asymptotes to help you out. Because the degree of my numerator is 2, it's a quadratic, and the degree of my denominator is also 2, I know that this horizontal asymptote is the ratio of the leading coefficients. So the way that I get 2 is by doing 2 over 1. And I don't necessarily need that 1 there, but this would be the equation of the graph. Now you can always put that into your calculator and just check to see that you did it right. And I did that, and I know that the question is correct. Okay, to summarize, horizontal asymptotes, ratio of the leading coefficients if the degrees are equal. Horizontal asymptote is 0 if the degree of the numerator is less than the degree of the denominator. And then the new one, there is no horizontal asymptote if the degree of the numerator is bigger than the denominator. If there is a point of discontinuity, that means that the numerator and denominator have a common factor. So this idea of fractions division is seen in all areas of math and even seen in the wonders of the world, such as the Great Divide. So I want you guys to work on practice questions number 1 to 7. The solutions to that is on D2L. And after that, you can go to your textbook questions. So that's the end of 9.2.